Good evening. Good evening, sir. Mr. John.
Charlene,
Yeah.
tell sir good evening. Let me see if he respond.
Good evening, sir. But I don't think him there laptop.
All right, a pleasant afternoon to, or evening now. It is 7 o'clock. Yeah, evening, guys. As per usual, I would give you a couple of minutes to start out and to get yourself settled. Some of you were coming through the hustle and bustle of the traffic, and some of you coming from one class to this 3-hour class. I tried to give you a few minutes to just sort out yourself. I do trust that you had a good day today.
Sir.
Say it again.
A chunk me have to jump in.
Boy, I have to go watch now, you know, because it look like you're taking this thing for a habit now.
Sir, me I forget home and not be pushing a Spanish town and them mucky water there, sir.
I hear you. Anyway, this too shall pass, and you know the blessing will come upon you one of these days, so you can buy your X10. And of course, you know, you can't splash me when you have that. You have to teach a little OneDrive, you know. And
Amen. Amen.
Yeah, man, receive it. Yeah. So, you know, I really hope that today was a good one for you and that you are now ready to go. We have quite a bit of stuff to cover. And we are moving into Unit 3 today, for sure. In reflecting, something came to mind and I think I want to execute it. I'm going to give you a question to do for me as a quick warm-up, just to see how much you guys are getting yourselves prepared. Oh, speaking about preparation, so I've been in several meetings today. Matter of fact, the last meeting I came out of was at 6 o'clock on campus. I went into work today, and there's a lot of talk about coursework, that next week is common coursework. And I'm going to tell you straight up, my headspace is not even there for next week for the common coursework. So more than likely my coursework for you is going to be the week after. So let me just say, so you would hear, I'm sure you'd hear from your other classes, your lecturers talking about coursework piece for next week.
Coursework or mid-semester, sir? It's
same one, mid-semester. I'm from the old school, so I'm going to call it coursework. Mid-semester, yeah man, that may talk. But my headspace is not even there yet because I am now dealing with registration of students who are coming in and continuity and differentiation. Yeah, that's where I'm at. And my headspace is really not there yet. So I can tell you for sure, yours won't be next week, but yours will be the week after. Now, let me say it one more time. Sir Shan, not going to give you your coursework piece, your mid-semester, same difference. Next week, because his headspace is not there. School's supposed to begin on the 25th for the first year students, and I'm currently doing registration for the first year students. So I'm not going to have the time to sort out and do up on them wonderful, fabulous looking stuff. But for sure, the following week, as night turns to day and God's sparing life, we'll be doing our mid-semester. Now, I will talk to you about how we will do mid-semester exams. I'll talk to you about ensuring that your cameras are on. I'll talk to you about, you know, some of the other protocols that I would want you to do for the stuff. So maybe sometime next week we'll do a little mock of what it is that I would expect of you for the exam, etc., etc. But for now, though, I want to give you a question to work for me, to differentiate from first principles. And I'm going to ask you to write it. My system taking a while to come up. So I'm going to ask you to write the function for me. And then I'm going to ask you to differentiate for me using first principles. And the question is, did I give you X cube before? Is X cube on the document that I gave you? Check for me, somebody.
Yes, sir, it's on it.
X cube is on it. All right. So what I want. All right. So what I want you to do for me is X cubed minus 1. I want you to differentiate for me X cubed minus 1. X cubed minus 1. Okay. Did I give you the solution for X cubed?
No.
And did he give you the solution for x cubed? Somebody check for me, please. Yeah, no, maybe so. Somebody not talking to me.
Sir,
Yeah, hear me?
I'm hearing you now.
Differentiate f of x equal x cubed from first principles.
Right. But did I give you the solution to it?
Yeah, number 9.
All right. So what I want you to do is x cubed minus 1. So look at that x cubed for me and do x cubed minus 1 for me, please. I give you about 5 minutes and then I'll
Sure,
check in
one
on you.
and may I use, lunch I eat now.
No problem. I mean go do the same thing too. All right. Start for me, please.
All right.
I'm gonna mute. Okay, no problem.
Never mind.
Is anyone finished?
Think so.
All right. And what do you have as the answer?
3x squared.
How confident are you?
Extremely confident.
All right. Yay. You better use one on more often here. Is there anyone in the class that agrees with Calvito?
There's her.
I'm just asking if there's anyone else in the class that agrees with you, but apparently they're still working. So let me give them 3 more minutes. Yeah, let me give them 3 more minutes. That's all. I'm not rushing it. So they really want you to let me know what it is that you're not understanding in this. Take your time.
Sure, evening. Just to confirm, you said no, you said x cubed minus 1, right?
Correcto.
All right, thanks.
Think I'm finished.
What's your answer?
3x squared.
All right, hold on for that one soon come. What the rest of you said? Come on, you need to hurry up and work.
Good evening, sir. May I see the question, please?
Oh, I didn't write it. It is x cubed minus 1. First principles differentiation. X cubed minus 1. Noted. All right. Charlie, Andrew, Kelvito, congratulations. Question is, all right, let me just take this out since I have it up top. Do I have it here? Yeah. Let me just take that out. So that's the question. And its answer.
Sorry.
Yes, please.
When you're expanding, does it matter what position you put the X and the H?
All right, sit again, Charlene. You're muffled a while ago. It doesn't matter where what?
I'm saying when you're expanding,
Mm-hmm.
like for example, in line 2 there, does it matter where you put the X and the H?
No. You could have H squared X. It doesn't matter really.
Okay.
Normally I put it in alphabetical order. So you would see you put H X squared. I don't know why I did it like this time, but normally when I'm doing a question, I put it in alphabetical order, but it really doesn't matter. That's the truth. So I'm going to let it stay like that to show you that it really doesn't matter. But good question. So for those of you who didn't hear what Charlene's question was, she's asking if it makes a difference if I have 3x squared h to the first, but she has it as 3h to the first x squares. It really doesn't matter. Tomato, tomato. All right. So you recognize that the function x cubed and the function x cubed minus 1 has the same differential, don't?
Yes, sir.
What do you think the differentiation would be for x cubed plus 10?
I believe it would be the same.
The same,
Okay.
sir.
Very good. And if I'd given you x cubed minus 5.
Same results.
Same.
Very good. Same result. But what if I gave you x cubed minus x?
No, that would be different.
But tell me why, Andrew. Just put it in your terms. Go ahead, Andrew.
Okay, from what I have deduced from the first principle, once it is a x, once it's not once it's not a whole number, and it's a x, whether it be 3x or 2x at the ending, usually the result would be different. Give me a minute, and maybe I can even give you the answer just by what you told me.
No. I don't want you to work it, It's just that I wanted you to see if the trend is going and you're moving on the right trajectory. So don't work out nothing. Just continue talking. You're on the right trajectory. So continue, Papa. And he's gone. All right. So anybody wants to pick up from where he was at?
No, I'm not gone. I was looking through something, but I noticed the trend. Usually the equation for the first x equation, that usually changes while the rest remains the same.
Okay, so it changes when I'm talking about a variable, right?
Right.
Okay, good. Okay, so it's very good. So I just wanted to help you right here. So it doesn't matter what I gave you right out here. So once it's a constant, it does not matter. If it is a variable now, where you have to put the incremental change, then it matters, right? So what I'm saying to you, if I give you x cubed plus 1, the result is going to be 3x squared. If I give you x cubed minus 4011, it's still going to be 3x squared. Once it's a constant that follows thereafter, it really doesn't matter. I have a nice story to tell about that constant. You notice I work using the word constant, sounding big, constant. Yeah, that constant, it doesn't make a difference. It is there, but it's not there. It doesn't add anything to the conversation. It is a placeholder. Yeah, you know that the person is there, but you know the person is there. The person is not going to contribute to the conversation, so you don't even have a clue what is inside the person's head. All right, but you know that person is taking up the space of somebody else who may want to speak.
So them just they figure more work.
Them just they figure more work, or for just show them presence, but not more. All right, very good. Now before,
Sir,
go ahead,
one
Papa.
moment. Yeah. What? Yeah. what I've noticed is what whenever you give us an equation to work out,
Mhm,
for instance, the one that says 4x squared plus 2x,
mhm.
right? The answer is usually that the 4x you would usually double the number, and the x would just and the square or the incremental variable would actually go down, and the x would actually from the two would just disappear, so to speak.
All
I,
right,
I, I
Andrew.
don't know if I'm explaining myself properly.
No, Andrew, I hear you, but you're one of those people that I don't like. You know, when you go to a movie, and because you watch a movie before you just talk about the movie, so the suspense not there anymore. That is you. But very good, Andrew. Excellent. I'm proud of you, Papa. No, man, I'm really proud of you. And let me just pause and just say to you what it is. And I know Andrew is working because mathematics is the study of patterns. So when you want to see any pattern at all, study maths. Now what Andrew has done, yeah, him talk out the story. But I'm happy when he talks the story out. You know why? Because Andrew is doing the work and he's looking and he's seeing the pattern. No, let me just translate what it is that Andrew said. Andrew said the question with the 4x, and that's why I scroll up to it. The 4x squared plus 2x. So I recognize that the number in front of the 4x squared is going to be doubled, and the other one is just going to be that, and it's going to pretty much remove the x from it. No, very good observation. Now let us see if what Andrew said is right. Him said that 2 years are going to be doubled. Let's say if we have 4x right on here, so Rockstone are true. Real talk. Let me say no. And him just take off the x right here and him get the 5. Never see if Andrew's right. So that means that 7 you go double. So you go have 14x and then you go drop off the x, so you make 14x minus 3. Rockstone, the boy bright. You go try one more, you know. And if it work the one time you saw, something. So you go double that one here, and then double that one here, you go get negative 6x, and then drop off the x, so it's negative 6x minus 2. Whoa, negative 6x minus 2. Him taught the story, you know, but there's one piece of the story that he missed, and I'm here now to unravel the true essence, the plot behind it, since I am the director. Now, before I get into that, guys, I'm feeling really very excited. I don't know if you hear the excitement in my voice, but I'm feeling the excitement because this is where I want my class to go. This is where I want the class to go. I don't want you to become passive learners. I want you to become very active in what it is that we do. So you do the work and you look to see, then a whole story get something here. Jesus, me get that question upon first principles and how much line me have to write, right? Not that Andrew going to shortcut you something, you know, because first principles you can't shortcut. He have to do everything to show what is happening. But the mere fact that he's seeing what is happening suggests then that when he gets the question, he can have an idea what the answer is supposed to be like. You know, quite a number of you don't know what I look like. Many of you may not know what I look like.
Show yourself, sir.
Sir, make Charlene smile tonight. Show your face.
No, Jermaine is here. So who is it? No, I know one. I know two. This is not good. Hold on. It is not good. It really isn't good. Really isn't good. I promise to do it next class. Really isn't good. So there are
Sorry,
two
I'm gonna
students.
put on your Sunday best.
Mr. I'm to tell you, man, I'm brush all teeth too, you know. Watch you know. Guess what?
He must dress up for Charlene and look presentable.
Charlene, pretty car eye, and me I drive X6, so I mean. All right, guess what happened though? There are two students that I can actually see on the road and pull out and say, yo, well gone. And the rest of you, maybe if you're on campus and hear this annoying voice, I say, hey, I'm Mr. Shandat, you understand? But come next week Thursday, this Thursday rather, all cameras are going to be on, and we're going to have a Zoom party, a Zoom calculus party, all right? So
I was
You
trying
know
to talk about all cameras.
Kelvita.
Yes.
Make sure it says C1 first turn on, you know.
No,
It says
my one of the
trouble.
last one I turn on,
Mhm.
and it must have to be after,
Mhm.
after,
No,
after.
no class now go on then.
Oh, sir, next
Yes,
week,
yes,
Thursday, my camera not go work.
It now go work. Darn. So guess what? You turn on yours now then. All right. So, I can understand that, you're in the confines of your home. Some of you just come home from work and, you kind of feel relaxed to come to this nice class and thing. But anyhow, so Thursday coming, we can meet and greet and we can have a little party. I'll take out my wine glass and I can, we can, Jesus, but I'm being recorded. I'm
No,
gonna go
you're
share.
talking, sir.
Yeah,
No,
me know.
talking.
Yes, Sasha, you can, the roommate in the class,
Sir, Clean, just can't stop the recording.
Sir,
Yes, Andrew.
I think I
Yes.
figured out the rest of the story.
If you got the rest of the story, let me hear, because it's the story that we're going through tonight, So let me hear. Use this one here that is projected, Andrew, and let me hear if your story right.
Well, another one, them they look upon is the last question.
No, man, but other one, I want to do. If you figure out the story, it will work with any one of them. So work it with the one here. And he gone. He's gone.
The answer doesn't equate out to be the same thing.
It doesn't. All right, that means your story not work out there. But don't worry about it. Don't worry about it. All right. Now I'm going to move on to Unit 3. I'm moving on to Unit 3. The little exercise I just did a while ago in terms of questioning, is it the same? Are you seeing a pattern? It's moving into my other story.
Question, sir, before you
Yes,
move
Sash.
into the
Yes,
story.
Sash. Go ahead.
What I noticed with me, I was box shuffling when I started doing the working out. So the cube, no matter the power that it's in, that's when you would see it beside the hx. That's the amount, right? Just want to confirm.
Yeah. So you talk about the power right here. So we'll be in front of the hx. In front of here. So that's what you're talking?
Yeah.
Yeah. Andrew, I'm a little curious. So very good, Sash. I'm a little curious, so Andrew. Unmute for me, people. So we have been doing this stuff, and based on what it is that you're saying here, with the exception of that one, I'm going to come back to this topic, because I have some fractional ones that I need to trouble you guys with. So at the start of class on Thursday, I'm going to give you another one question, and so forth and so on. So Andrew, if you look at this, you're saying that in this case, this one is just going to be, this going to double up. So if there's an imaginary one right here, so this is going to be double up and it's going to be 2x. And this, there's nothing right here, so the answer is going to be 2x. Yeah, like so. Tell me now, how would you account for this answer? Oh no. How would you account for this answer here to be 3x squared, though, Andrew? I'm curious. How would you? So you work that question, the x cubed, and then it got 3x squared. Is it that your theory broke down at some point in time? Because you're saying that with this one, or is there something else with this one? You're saying that come on, not this one. You're saying that
Sir, I keep seeing something flashing in this on the screen.
Yeah, all right, let me stop share and then reshare again. That's the only way I can get rid of it. Yeah, it can be annoying. All right, so go on now. Right. So I want you to tell me, Andrew, and trust me, when I used to go teacher school, them talk about the investigatory approach to the teaching and learning of mathematics. Sarah, do some investigatory approach tonight. Andrew, unmute.
Yes, I'm here. I'm listening. I'm here.
But wait, talk to me. Tell me what is happening here, son.
Okay, what I've noticed is that whenever it is x squared, right, the theory is sound, but once it goes on to x cubed, all right, there's a change because the variable is now times again. If I get what I'm saying.
Yeah,
right.
but so it's not doubled again. That's what you're saying. It's not doubled this time.
No, it's not doubled. It's tripled.
It's tripled.
Right.
Okay. All right.
So in most of the equations, when you have x squared, you would have 2h where is it? You would have 2h x squared. But no,
Mhm.
it moves from 2h x squared to 3h x squared.
Okay. All right. Press pause. So you say, so what if I give you x to the fourth, and what do you think the answer would be? Or anybody else?
4x squared?
All right. Okay. All right. Very close. Very close.
No,
Very
no, no.
close.
Hold on. No, it wouldn't be that. You'd have to go double it for. So more like I would say 8x squared.
Go back to the first answer.
4x squared?
All right. So that one is closer. So I'm going to say press pause on that. That one is much closer. And okay, yeah, press pause on that. That one is much closer. Very good. I'm not going to keep the suspense any longer. I'm going to stop here with this one. Then I'm going to go into my new story. New story this morning. So, new share. All right. So you notice now I have rules for differentiation. I have rules for differentiation. Now, matter of fact, Kelvita put on a chicken bone. I want you to pay attention. I want everybody to catch this now, because guess what? Is if you don't understand differentiation and integration, calculus 1 becomes a breeze. And 25% of calculus 2 is already done if you can differentiate and you can integrate. Now I've shown you first principles differentiation. Here goes now. We are onto the other types of differentiation. Hear the story. I'm looking at the chain rule. Now, life is filled with a lot of rules. Big man like me, they might tell me, say me can't come out of my yard on Sunday. I'm going to go in on Saturday. I'm going to turn to my yard from 8 o'clock a weekday and 6 o'clock on them time. Yeah, we have rules. Father God gave us rules. Mathematics has rules. So let us look at the chain rule. If I give it a function, y equals x to the n, this is a function. Just like I give you y equals x cubed and y equals 2x squared plus 5x plus 6 and y equals x cubed minus 1.
Stop liquor. Bigify.
Bigify.
A bit more.
I'm going to bigify this thing because I want
Right,
to
cool.
see it. All right. So what is going to happen is we are going to give me half a second, please. Half a second.
Sir, if you talk, me not hear you.
No, man, I did after 2 seconds. Sorry about that.
2 seconds.
Right. So, so life is filled with a lot of rules. Now, watch this. This is a function. The function is given by y equals y to the n. Rubbishness. Y is equals to x to the n. That's a function. This is a base, x, and the power is n. Y equals x to the n is a power. Now, when I'm finding my dy by dx, my rate of change of y with respect to x, my differentiation, my gradient, my slope is so much name it have, differentiation, dy by dx, my gradient, dy by dx, my slope, dy by dx, the rate of change of y with respect to x, I'm going to take a number here up here so, and I'm going to put it in front of the number down here so, and I'm going to reduce the number up here so by 1. So if you look at the one that we just did a while ago, x cubed, see here, x cubed, that 3 here, I go multiply in front of the something here so, and then we're going to reduce this one here by 1. So we can get 3x squared because this is 3 minus 1. So I get 3x squared. Let me let me put something else in here. Copy. Let me just show you step by step what is happening here. I paste that here, and I'm going to put up here. And I'm going to put that in blue to show you that that's not the final answer. So what it is that I have done, watch me. don't blink, you know, you blink, you lose it. Y is equals to x to the n. Let me spotlight. Y is equals to x to the n. The power is going to come down and multiply in front of the coefficient here. See it here, so the n, and then I'm going to reduce the power by 1. See it here, so minus 1. So the rule for differentiation is going to be y is equals to x to n. dy by dx is going to be n x to the n minus 1. The power becomes the coefficient, and the power is reduced by 1. Remember that. Look at the second to last question we did in first principles differentiation. Y is equals to x cubed. That 3 I'm going to use and multiply. It becomes the coefficient. See it here, so in front of here, so see it right here, so. And then I'm going to reduce the power by 1. So it's going to be 3 minus 1, sir. So it's every time you can take the power and put in front of the something. Yeah. And every single time, sir, you have to tell me, say you can reduce the power by 1. Yeah. So this answer is going to be 3x squared. Now what? Talk truth. You could do this question in 2 lines, but sir gave you the something for do in about 20 lines a while ago. Is all life unfair? Is all life unfair? Watch me again. Y is equals to
Not
x to
unfair,
the
sir.
very good.
Not
I'm happy for
unfair
that.
because we need to know the working out
First
and how we
principle.
come to the
Very good, very good. And what is true? For first principles, it is going to be longer because just like when we did the intuitive approach to evaluate our limits, you would agree with me was much longer than just assuming that the number is x and just substitute it to that. Boom, you get your answer. The intuitive approach, I have to do the question several times to the left, several times to the right. You understand? And sir normally go 4 times. 0.9, 0.99, 0.999, 0.9999, and then sir can go 1.0, 1.1, 1.01, 1.001, 1.0001. So 8 different times I have to go to the calculation, as opposed to just say, assume that something is equals to 1. Boof, you get your answer, right? So from first principles, the intuitive approach is actually from first principles. That will take a longer time, but you have to understand that. And I'm so happy that I spent so much time doing the first principles, because when I got to piecewise function, when we're supposed to be, oh crap, Jesus. All right. So, you know, Sandra, you're supposed to start. As I talk about piecewise, I was supposed to show you how to graph some stuff, but never mind. Let us go. I'm into this already. Let us go. Please remind me, I need to show you some, I need to give you a software tonight to play around with, or if not, Thursday business. We can do that on Thursday. Let me just continue my story. All right. So when we got to piecewise function, I never had a great challenge with the class because people understood the assignment. Why? Because people did the homework from before. So let's go again. Y is equals to x cubed. You're taking something here, so you put it in front of the something here, so, and you're reducing it by 1. And you're reducing it by 1. And you're reducing it by 1. So y cubed now becomes 3x squared. 3x squared, sir. Why, sir? Me never have to do this, you know. I only do this to show you the reduction, because this is what I had for my answer. 1 line. Watch me. So this is a question that I think we got also, because what I did, I wanted to bring across a point. So I think I used the questions that we had in the stuff to show you. All right. So let us go. Now, what I want you to do for me, hold on a second, please. What I want you to do for me, I want you to, for those of you who are wearing a chain, I want you to pull that necklace from your neck, please. If you're wearing a bracelet or an anklet, I want you to look at it. Or if you don't have a chain, I want to visualize something. Visualize a chain. And notice up here, I did say chain rule. So what I want you to do with that chain, I want you to visualize it and recognize that that chain, what there? Let me not even tell you. Let me ask you, what do you recognize with the chain? Or with a chain?
You have links, sir.
Very good. You have linkages on that chain. All right, watch me. Negative 3x squared is one link. Negative 2x is another link. Negative 3 is another link. So that's what is called a chain rule, because I have linkages here. Why am I doing this with you, sir? Why I talk about chain in a math class? How can I foolishness go in a math class, sir? Because I want you, whenever you see the chain rule, to recognize the chain rule. Just like when you go to supermarket and you see chicken, you know, say a chicken. And when you say frog, you know, say a frog, hopefully. All right? So negative 3x squared minus 2x minus 3, when I'm differentiating, I must use a chain rule, because this is one link of the chain combined with another link of the chain. Because watch this now. If you're a negative sign here, this negative sign link this term to this term. And a sign here, link this term to this term. So we're talking about the chain rule. All right, so we get the chain rule now. Make we differentiate. So when we're differentiating using the chain rule, we are differentiating each link by itself. Individually, we are differentiating the terms. All right, so let us differentiate this term, negative 3x squared. Remember, y is equals to x to the n. Dy by dx is going to be equals to n x to the n minus 1. The power is going to be used to multiply what is inside here. And then I'm going to reduce the power by 1. So watch this now. This 2 is going to be used to multiply the coefficient here. So I'm going to get 2 times negative 3, and then I'm going to reduce this by 1. And then, is this raised to a power? I'm not seeing a power there. What does that mean?
That one. In
One,
sir.
by one,
sir.
Excellent. I like this class. Excellent. So there is an imaginary 1 up here. Look, there's an imaginary 1 up here. So what is going to happen is that I'm going to use this imaginary 1 to multiply this negative 2, and then I'm going to subtract 1 from the power. 2 times. Rockstone, but I'm not seeing anything. Is there an x right here, sir?
No, sir.
Can I put an x right here, sir?
Yes, but it would be 0, right? Wouldn't it?
What
To
would
the
be
zero
0?
power. To the zero power.
If there's
Say it one more time.
there's
It
0.
should be x to the zero power.
No, sir. Me think me have the best class to teach. Very nice. Yannick, tell me why it is to the 0 power though. Let me just stretch your legs a little. Why to the 0 power? Because
Anything raised to the zero power is 1.
woo,
No, isn't it 0?
no, she right. Don't cut her story short. No man, she right. Anything raised to the power 0 is 1. Every single time. Anything raised to the 0 power is 1. Every single time. 1 minute, please, guys. Hold on.
So that means it will remain the same, sir.
Yeah, man. So, Yannick is right. Anything raised to the power 0, every single time it's going to work out to be 1. Anything raised to the power 1 is itself, but anything raised to the power 0 is 1. All right. So see it there now, right? So this x is raised to the first power. Then, sir, every time you saw a variable and you know, so no power up there, so you can assume 1. Absolutely. And every time you see a whole number, you can assume say it is a variable written behind it with the power 0. Absolutely.
Those adventures.
Same way, so. But sir, Mr. Wagwan now. Oh, so that means if you differentiate this now, sir, based on the rule that you just gave us, this is going to be 2 times -3 is -6x because you subtract 1 from the power. And then you're going to have 1 times -2 is -2. So you're going to be -2 alone because this is going to be 1 minus 1, which is 0. But what I want to work out to be though?
1 over
Negative
x.
3 times 0 will give you 0.
What I want to go be
And then
0?
minus, right. But now the
Oh,
question is, won't it be and it will be negative, and it will be x minus 1. Well,
1 minus 1, not x minus 1. It will be 1 minus 1 as a power.
no, I'm talking about the -3.
Yeah, man, no,
Negative
right, the
3x.
-3. Right, so it's gonna be 0 times -3 is just 0.
Hold up, look at it. Is it that every time you do this, you're going to get and is 0, 1, 2, and if it was x to the whatever 4, the powers would be 0, 1, 2, 3. If there was a third constant, you get me?
I get what it is that you're saying, but it doesn't always. So this is a trinomial, and the trinomial is written like that, where it's 2 as a power, then 1, and then 0. But it doesn't always. It's not always written like that. It's not always written like that. That's what I'm saying, Kavita. But good observation. I'm happy that you're seeing that. But it's not always written in descending powers of x. Them can mix it up, and trust me, when you get into the meat of the differentiation, they can say, oh well, then mix it up. This is fried rice, egg, rice, noodles, every god almighty something in it, but it tastes nice though. All right, yeah, man. Somebody was trying to come in. Yannick, you was trying to come in. All right, maybe
I
not.
know which me that goes a sir, so that's stop me.
All right, then cool, no problem.
Anika says she lost in the chat.
Oh, sorry, jeez, you must watch your chat for me. Anika, you lost. All right, which bus stop is it?
Sir, I'm not even at the bus stop.
You're there at the bus stop?
I try to reach the bus stop.
Yeah, try to reach bus stop. All right. Tell me no honey bunches. Sorry, I'm just going through the chat. All right, okay. All right, no problem. All right, let me just finish the explanation here, Anika, and then I'm going to go over for you because I really don't want anybody to be lost. This part is a nice part. Trust me. The part is nice.
Sure. So just to
Yes,
confirm,
Papa.
where you have the 3x raised to the power 0 is basically just an imaginary x then.
And that's why I put it in one ugly color. Sorry, I shouldn't say that. That's why I put it into a light color. You notice it's not. It's when you go to one of them schools where the rival wear that kind of color there.
Yes, sir. We know
we know.
It's ugly, sir. It's ugly.
It's ugly. And put like a black with it. It's uglier.
Try get no. Hold on. A green or black, can I say, sir?
Yeah, purple.
Straight up.
Sir, in other news, sir. Me have a question. It might not affect the price of rice, but how comes that become +0, not -0?
La-di-dee-la-di-da. Yannick, if I subtract nothing from you and I give you nothing, does it change the matter?
No, that's why I'm saying affect the price of rice, but
Right,
based on what the symbol that would coming down with.
Right. Just for your sake, I'm going to change it. But yeah, you're correct. You're correct. But you're right. It's not going to change the price of rice. It may change for the price of bread. One bread is almost $500 to blow. But anyhow, let's go. So, Anika, I recognize that I need to come back to you, but don't worry. I'm just going to go through this, finish off this piece, so I can finish the story and then I can tell you the story one more time. Watch this now. So remember, anything raised to the power 0 is 1 every single time. That can't change. Can't change. The price is constant. Anything raised to the power 0 is always 1, right? Now, let me go. Oh crap! Let me go back to let me go back to this question. So I did ask, oh Lord. I did ask Andrew if this piece, if anything here so would change for this piece. And him say, no, sir, it wouldn't change because there is no, and him couldn't find the word. I said, variable, yes, sir, that's the word. There's no variable to here so. And I had used a word for this. Anybody can remember the word I used?
Sir, constant.
Very good. I use the word constant. Watch me. So you recognize any constant I put right here, so still won't change the price of anything because there's something going to come out to be this. That's exactly what we're talking about. New share. That's exactly what we're talking about. That's not it. New share. This is it. This is a constant. Sir, how do you know? How do you recognize a constant? It stands alone, just like the minus one I gave you. And now I'm giving you a minus 3. Then, sir, I own a minus a constant? No, if I'd given you a plus 3 or a plus 1, it will still be a constant. So a constant has no variable added to it. Then, sir, you put x to the 0. Yeah, I only put this here to show you that there's an imaginary variable on this side here. All right, watch me now. Please note the differential of a constant is equals, oh crap, is equals to 0 every single time. Eraser. The differential of a constant is equals to 0 every single time. That can't, what is wrong? That can't change. The differential of a constant is going to be equal to 0. Sir, why? Me hear you say it, sir, but why? Look on it. See the story here? 0, because a constant is going to have a variable raised to the 0 power. A constant, because this x to the 0 is 1, and 1 times negative 3 is negative 3. So putting the x to the 0 up here, so not going to change the price of anything. Not changing the price of nothing at all. All right? So that's why we don't even put it here, because it's neither here nor there. It does not affect it. But in the back of your heads, you should understand that it exists and it is there. Watch me. Why the differential of a constant is always equal to 0? Because when I use this 0 to multiply the coefficient here, is going to give me 0. So the differential of a constant is going to always be equal to 0. Never, ever, ever, ever make a mistake and find the differential of a constant and put anything else other than a 0. Every single time, barring none. The differential of a constant is going to be 0 every single time. All right. So therefore, this is going to become now negative 6x to the first, because 2 minus 1 is to the first. But sorry, you have to write to the first? No, you don't have to. Because when we're not seeing to the first, we know that the first is there. And 1 minus 1 is 0, sir. Then, sir, why never write 2x to the 0? Because we know say x to the 0 is 1. So it's just minus 2. So this now becomes my answer. dy by dx is going to be equal to negative 6x minus 2. And that's one of the questions that we got. That's one of the questions that we got. All right. Now, so Nikki Boo says she don't leave out of the house yet. And she's leaving and don't know where her destination is going. She don't know where she'll go. So we can go again. But let me start from here. The chain rule says the function is y equals x to the n. When I'm differentiating, I'm using the power to multiply the coefficient here, so. And I'm reducing the power by 1. Watch me. This n becomes here, see it here. This n is then going to be reduced by 1. X cubed is going to become 3x squared, because it's 3 minus 1, 3x squared. And that's it. This one becomes 2 times negative 3 is negative 6. See there? I'm reducing this by 1, so it becomes negative 6 to the first power, or just negative 6x right here. So, and this becomes to the first power, 1 times negative 2 is negative 2. I'm going to reduce that by 1, so that goes to 0, so it's just negative 2. This is what I just did a while ago. The point is you can move directly from here to here. All right? So what I did right here was just to show you the steps. What I did first is to show you that this x is raised to the first power, see it right here. So what I also showed you is that this constant, negative 3, has an x to the 0 behind it. And then now, when I'm differentiating, this 2 becomes 2 times negative 3 to give me negative 6. And I'm reducing the power by 1. That's why I have 2 minus 1. And then I'm going to have 1 times 2 is this 2. And I'm reducing the power by 1. So you're going to be 1 minus 1. See it right here. So, and this 0 times this negative 3 gives me 0. And Yannick says, sir, you're the plan. Put it as negative 0, you know, because a negative, okay, so, and a negative, so the constant is negative 0. Anything raised to the power 0 is 1. And the differential of a constant is equal to 0. So what is going to happen here is 2 minus 1 is 1. So this becomes negative 6x, and this becomes just negative 2. Go ahead, Yannick. Your hand is raised.
So yes, so, sir. In terms of they write the question without the equal to y, right? And they still just differentiate. You can choose to use a chain rule in terms of you would just equate it to y, just as I would equate it to fx for the first principle.
Right. Excellent question.
Okay. Okay.
Excellent question, honey. And I'm really very proud of you guys. It suggests to me that you are really very active learners, and the brain juices are flowing, and that's what I love. And the rest of you who are not fully awake, I'm going to beg you to allow the juices to flow. It is much better when the juices flow. Trust me. Watch me. Very good. So based on your question, Yannick, I am going to write my question like that. It says differentiate 4x squared minus 1. So what I'm going to do in my solution, I will have to so the question can be given differentiate 4x squared minus 3x minus 1. You don't know what that function is equal to. So you're going to let it to be equal to f of x, or you can let it be equal to y. You can let it be equal to anything away from x. If you want it equal to z, you want it equal to q, r, a, b, anything away from x, the variable that is defined in the function. All right. So if it doesn't have if it doesn't have a title, you have to give it a title. What is the title, sir? F of x, y, q of x, whatever else it is. All right. So I'm going to leave that there. Anika, unmute for me, please, honey bunches.
Yes, sir.
Is it clear up?
Yes, sir, it is.
All right, mute. All right, thanks, honey. Yes, Papa.
So I have to show the working, especially x to the power of 0. That was
No, man, Krishna. Remember, but I would say, I am only doing this here now because I'm only now introducing the chain rule to you. So I want to show you what happens.
okay.
Yeah, man. So as we go, you will see me start shedding these little something inside here. So shedding them. All right. Let us look at a third example. So it says differentiate 4x squared plus 3x minus 1. So Yannick asks the question, sir, then what if them don't give you? Fine, they never give you one here. So no, I decide to let the function be equal to f of x. So I'm going to let f of x be equal to a function. So it's me working the question, you know. So I work the question now. So f of x equals to the function. But sir, how you call this dy by dx? That's what you call the first one dy by dx. The rate of change of y with respect to x. Good question. All right, I have prepared some notes for you. For unit 5. Unit 5, I think it was. I have done some work for you. Okay. Let me just copy something from unit 5 and paste it inside here. Put off path. Where do I put it? Let me just drop it here and see if it looks good. All right. Look here. So f of x is equals to y. You know this. F of x is equals to y. Then sir, g of x is equals to y too. Yeah, man. And h of x equals to y, and p of x equals to y, and q of x equals to y. All of it something with x is equals to y. So this equals this. So we can use a 1 year or we can use a 1 year. Now for the first derivative, if we use the 1 year f of x, the first derivative, like we're finding here, so it's going to be f dash of x. And if I use the y, the first derivative is going to be dy by dx. So these are called the first derivatives. All right. Now, when you see f double dash of x, it means that I'm finding the second derivative. And when I say d2y by dx squared, it means that I'm finding the third derivative. So therefore, if I'm finding rubbishness, I'm finding the second derivative. So therefore, if I'm finding the third derivative, what does this one become? Anybody hearing me?
F with 3 strokes, X in brackets.
Very good. And what does this one become?
D cubed Y
over
dx cube.
Very good.
Sir, is it that you have
All right. One of us internet is very unstable. So be mine. Go ahead, Sash. Is it that I have who?
You hear me, sir?
All right, go ahead again, honey.
You have second when it's supposed to be third.
No, man, this is a second derivative. Hello? Right, so this is a double stroke. I think our internet is unstable. So this is a double stroke, so it is going to be the second derivative. And this 2 here and the 2 down here suggests that it is a second derivative. And if I'm speaking about the third derivative, I would have f3 dashes up here of x, and this will be d cubed y by dx cubed. So these numbers here and the number up here, so must be the same number down here, so, and it tells you what number derivative that we are talking about. You notice that there's a 1 up here, so but we're not write it, and there's a 1 right here, so we're not write it. So dy by dx is actually the first derivative. All right, and so we can use dy by dx, or we can use f dash of x. Provisionally, yeah, f dash of x. Right, so dy by dx or f dash of x.
Sir, all of them letter there just decode something out of my brain because.
So, sir, the chain rule would apply to the first derivative.
It also applies to the second derivative, and the third derivative, and the fourth derivative, and the fifth derivative. So what I'm doing is just introducing to you the different rules. So the chain rule is just one of the many rules that we're going to be talking about tonight. So the function, the function is what is going to be given by this stuff. Y is f of x. I can give it a function in f of x, or I can give it a function in y. If I give it a function in f of x, when you find the first derivative, you're going to denote it as f dash of x. If I give it a function in y, to find the first derivative, it's going to be denoted as dy by dx. If I function is given in f of is given in y, it's going to be d squared y by dx squared.
Sir,
And
we
it
just
goes
said
on
it
and
a
on.
while
If I
ago,
give-
just drop.
Sir, your internet drop out,
Internet
sir.
drop out from way.
All right, hold on.
So I know me on the problem then.
We don't want a long time for my internet.
Which internet you have, sir?
Oh, so it's me then. Who we use again? What is the name? Digicel.
Oh.
Yeah. I think
I'll
maybe
leave
me.
class and come back to you, say me.
All right. I'm me then. All right. Hold on. Let me just check the logo. But the bars are full. All right.
I need to reset.
Yeah. I apologize. I don't want to reset nothing, because I go just take a pulley for my time and class will go on nice.
After class,
Alright.
you can do that, sir.
Yeah?
After class, you can do that.
Yeah, after class. Yeah, I don't want to disturb the class. All right. Now, Kelvito, come back to me, honey.
Sir, I miss out, sir.
You missed
Because
out.
I left
Oh,
the class and come back.
all right. Don't worry about it. Don't worry about it. Don't worry about it. So what I'm saying to you, work with me. What I'm saying to you is that I have several options of naming my function. I can name my function, for example, as f of x. If I do name my function f of x, and I ask you to find the first derivative of the function, you are going to title it as f dash of x. If you're finding the second derivative, it's going to be titled f double dash of x. If you're finding the third derivative, it's going to be titled f triple dash of x. The fourth derivative, f to the fourth dash of x. If your function is titled y, to find the first derivative, it's going to be dy by dx. The second derivative is going to be d squared y by dx squared. The third derivative is d cubed y by dx cubed, d to the fourth y by dx cubed, d to the fifth y, and so forth and so on. So what I'm saying to you is, there are times I will give you the function in f of x. There are times I'll give the function in y. So I want you to be able to vacillate between the notations that I give you. I don't want you always to think that the answer is going to be in dy by dx. It can very well be in f dash of x. Then certainly mean the same thing, yeah. It means the same thing, But if the man them give f of x, nobody bright enough to give them dy by dx. The man them give f of x, tell them saying no, it is f dash of x. So this is just the nomenclature that I'm talking about, which is just the naming of the stuff. All right, let's go. So you notice this function here was in y. So when I do my stuff, I put it as dy by dx. This second question is also in y. So when I do my stuff, I get it as dy by dx. The next one now is in, I put it in f of x. So therefore, my first derivative is not going to be dy by dx. It's going to be f dash of x. But is this still the first derivative? Yeah. It's just the naming that I was trying to go through with you just now. And let us see if we can do the differentiation here. Remember, we're taking this, multiply it by this, reduce this by 1. 2 times 4 is 8. Reduce this 2, it becomes 1. 1 times 3 is 3. 1 times positive 3 is positive 3. This is to the first power, reduce it by 1, you get 0, done. The differentiation of a constant is always equal to 0. Boof. So then why don't I write plus 0? I don't need to write it. Unique said it's not going to change the price of nothing. This is my answer. Question done. Next. Jesus have mercy. I saw them teacher go on, Them give the nice questions in the class, And when you think that things are go right and you understand, no, bam, fraction. Fret not. Life is not always black and white. You have shades of gray. I notice I said shades. You have many of those. Work with me. But sir, you just talked about f of x and we're going to put in g of x. Remember, I told you f of x, g of x, p of x, q of x. The only thing you can have is x of x. Why, sir? Because x is already in the function. Anything them give, work with it. This is not bad because right here, so when I differentiate this, I know this is going to become g dash of x to find the first derivative. All right? Then, sir, we can do the first two something. We can do that one and that one, yes, sir. Me agree with you. You notice right here, that's a rearranging. So we're going to rearrange it. We're going to rearrange it. And look at what I'm going to do. I don't want to do that with you yet. Let me just copy something here. Because I really want you guys to follow what is happening here. I need to get me some laws of indices. Copy. No, let me just go ahead and just copy everything here. And now just go ahead and just do my pasting here. I'm going to paste and then, oh no, I don't want it to be in calendar. I want it to be in times. All right. Or okay. All right. So I want you to recall something here for me. Oh no. I want you to recall something here for me. A to the negative m. Let me turn it around so that you have a greater appreciation, hopefully.
So we're working.
I'm just trying to give you some notes so that when you go through the stuff, it is almost self-explanatory. So forgive me. All right, so watch this now. So 1 over a to the positive m is going to be equal to a to the negative m. That's one of the laws of indices. 1 over a to the positive m is going to be equal to a to the negative m. Let me take up this narrative because that narrative will go if I have it the other way around. 1 over a to the positive m is going to be equal to a to the negative m. Watch me. Because this is positive m in the denominator, I am going to remove it to negative n into the numerator. Or if I have a to the negative m in the denominator, when it goes to the numerator, it becomes positive. All right? So I'm saying this to show you this one. I have 1 over x to the positive 7. I can convert this by taking it to the numerator, and then it becomes x to the negative 7. Similarly, I have x to the positive 5. Watch me, just like this. I take it to the numerator, so it becomes x to the negative 5. So it becomes 3 times x to the negative 5. So I'm just explaining why I got this step here. So let me go again. 1 over a to the positive m is going to be equal to a to the negative m. Sir, how so? Once I have a positive power in the denominator, I can bring it to the numerator and that power becomes negative. Then, sir, this one and this one equal. Yes, the equal sign is so. This gives the same result as this does. This one gives the same result as this one does. And this is just the opposite to this one. If I have a negative power in the denominator, When I raise it to the numerator, I'm going to get a positive power. So let's go. So all I'm doing here is just rearranging, and hear me out. And I'm going to say this to you because this is very important. So important that I'm a little worried that, well, yeah, I'm a little worried that, and this is why I'm going through so much of my explanation. I try to explain the matters in depth so that you can have a fulsome understanding of what is happening, because I don't know what question CCCJ will send. I am a conceptual teacher, meaning say, I teach you the something from grassroots, you know how to do something. So whatever function the man them give you, you can twerk it because you know what it is that you're supposed to be doing. All right? You know what you're supposed to be doing. So you know how to differentiate, and they give you something in a fractional form. Don't worry. Convert it from the fractional form using the law of indices, one of the laws of indices. 1 over a to the positive m. If I have a fraction and the term under here is a positive, when I take it to the numerator, it becomes negative. See yourself? X to the positive 7 becomes x to the negative 7. You notice this one is the same one as this one here. And the 3 are the same 3 as here. So this is to the positive 5. Up top here, so it becomes negative 5. I don't need to change this one or this one. Now I get the question in a form that I'm accustomed to be using now. You notice that this is still g of x. I have not yet started my differentiation. All I have, what is wrong with this thing? I have not yet started my differentiation. All that I have done is just to rearrange, to make it in a form simple to work with. Watch me. Negative 7 multiplied by 1 gives me negative 7. But remember, I have to subtract 1 from the power. Now, because this is negative, it's not going to be 6. It's going to be negative 8. Because minus 7 minus 1 is minus 8. Be very careful with that. Remember, we always subtract 1 from the power. But when the power is negative, it's going to look like it is increasing. But it's really not increasing. It's actually decreasing. All right? And this negative 5 times positive 3 becomes negative 15. And I'm subtracting 1 from the power. So minus 5 minus 1 is minus 6. This is a positive power, so it's going to go down. 2 times a negative 4 is a negative 8x. And the differential of a constant is equal to 0. So this now becomes my answer. Are there any questions so far? I give you some do knows. Are there any questions so far?
No, sir.
All right, so do me a favor. I give.
Sir, hold on there. So, I think Kelly Brain just click a while ago. So if they say G dash of x, that means that when you're differentiating, you're going to have to write G double dash x.
The question was given as G of x. So when you find the first derivative, it's going to be G dash of x.
Yes. So what if the question says G dash of x and they said differentiate? Are you going to say G double dash of x?
Yes, man. Good. Right. Yes, man. Right. Kelly, you need to use the other hand. No, no, man. Very nice. Excellent. And students, this is what the whole teaching and learning process is supposed to be. Never ever sit down in a class and just try to catch everything from the teacher. Allow your brain to go. And it's one of two things, It's either the teacher going to say, no, you're off. Or the teacher going to say, very good, you're on the right track. But you have to make sure that you're following the trajectory. All right. What I'm going to do, I'm going to pause right here for a moment. And I'm going to give you an exercise. The exercise I'm going to give you should take about no more than 5 minutes. I went through first principles differentiation with you. We ended up doing 10 questions. One of the questions I just did a while ago, X cubed. I want you to look at all the first principles questions we have done. And I want you to differentiate it with the exception of the one that, with the exception of the one that, with exception of the one that was fractional, I don't want you to work the fractional one. Don't want with the numerator and denominator, don't work it. But you see, all the other questions, I want you to use the chain rule and differentiate it for me, please. I'll give you about 5 minutes to do that. Start now.
All 10 of them? Or 9?
Yeah, man, all of them, all 10 of them. Yeah, the 9 of them, because one of them was at different form, had numerator and denominator. We're not touching that yet. All right, start for me, please.
Hold on, sir. Where can I get the question to attempt?
That would be from what it is that we did in class last time. That would have been the last handout we did. When we did the first principles differentiation. What I want you to do now is to use a chain rule to see if when you differentiate the functions, you'll get the same answer as we have it on the in the handout on the first principles. You follow what I'm saying? So we did questions already with first principles. I want you to use the chain rule now to do it and see if you get the same answer.
So which question should I attempt? Which number?
Krishna, all the questions that we did on first principles differentiation.
Okay.
The handout that I gave you from before, Papa.
Okay.
Cool.
Sorry, can you go back to the double dash and the dash? So the rules, I should say. Yeah, that one. Thank you.
All right, I was trying to do something and I just made a boo-boo. Oh no. All right, hold up. Let me just get rid of this. I'm trying to keep the document pristine so that when you get it, you're not seeing any errors there. So, all right, so with that, that's correct. Okay, there you go now.
finished, sir.
Finished, sir.
How far are we with the questions? Are we finished with all 9 questions so far?
Not yet, sir.
All
Almost.
right, no problem. All right, no problem. I'll give you a couple more. Okay, next done. So all the questions that you did got the same answer as we did before when we did the first principles?
Yes, sir. The way they're actually easier though.
Man, it is. So it is far easier, but the other method must be learned because there are times, and I'm going to just tell you straight up. So for your mid-semester, they will give you questions for you to differentiate, and they will specifically say to you, use the chain rule, but they will specifically say to you, differentiate using first principles. If the question says to you differentiate and them don't specify which method to use the method that is easier. Say them here question, Lexton and the others of you to differentiate, and you don't say nothing about using the chain, using the first principles. Don't use first principles. First principles is longer. So only time you can use first principles is unless they tell you to use first principles. Take it from me. The only time you'll use first principles is when they tell you to use first principles. Outside of that, use the other methods that I'll show you. All right, so the rest of you, 2 more minutes just to work the questions. And I'm really hoping that you are working, and not sitting on and just waiting for me to come back. Work the questions, because I am going to be moving into some other questions. For those of you who are finished, oh no, do me a favor. For those of you who are finished, I want you to to work on these do now for me.
Sir, I don't know if you deliberately stop sharing.
Yeah, I deliberately stop sharing because I wanted to. I have the answers for this one here, and I want to take the answers off so that I can give you an opportunity to really work it on your own, without my interference with my answers. All right, so I'm giving you 3 questions. For those of you who are finished, I want to use the chain rule to differentiate those for me. I'm giving you 3 minutes.
Sir. Sir?
Yes, please.
We did the first number 4 already.
Oh, we did number 4 already?
Yes, sir.
All right. All right, let's do number 5 and 6 then. Thanks.
Sir, we also did number 5, sir.
Yeah, we just continue. Oh boy.
I want keep. I want to serve.
So yeah, look on the wrong paper, sir.
Clearly. All right, let me just.
Oh, so we can attempt fraction now, sir.
Yeah. Oh, those were the questions I gave you for the first principles, right?
Yes, sir.
Yeah, man. Right. You're correct. I did say that the first couple of questions that I have in the handout are the ones that we did for first principles. All right. Are we finished?
Yes, we are.
Okay, good. So let me just move on then. I'll just move on. And let me just do a new share.
Fraction ones. Do we do the fraction one?
Yeah, do the fraction one for me. Yeah, do the fraction one. Yeah.
Finish, I guess.
Benito.
Sir, for number 5, is that one that you have there, sir? That the F.
You have good eye. I never even noticed that.
I'm realizing something, sir.
Oh, I just realized that Sarah put out the answer. I was so confused.
What is it? You were confused a while ago? No, man. It's the answer that I put there. That's why I put it in red.
I realize now.
Sir,
Okay.
Yes, please, Ash.
Sorry, can you go back up a little bit, please?
I realize that I'm being confused with the what should be at the beside the answer, like what you have the f dash x. The f of x. What I put is I don't know if I was seeing the right thing. All right, so for example, question 4, I have y equal that question, and I said let f of x equal 7x minus 6, and then I put f of x equal.
They gave you the title for this already, Sash. They told you that y is equals to f of that. So you're going to find dy by dx. The only time you're going to put let something be equals to something is in this example when them don't give no title. Them just say differentiate and them gone straight into the function. You don't see no equal sign there to say that something equals something. So you have to go make something equal to something. So just like how me can look on you and say, yo, Browning, you girl. So you go turn to me and say, me have a name in a bedroom. So you need to name this function. So you see, because you see, there's no naming of this function. So how you know so the function is not named? Because it's not seeing something that says something equals something. So it's not a function that is already named. So you are going to name the function. You are naming the function. How you name the function? Let f of x be equals to that.
Okay.
In this case, you don't need to name the function because the function is already named. In this case, there's no need to name the function because the function is already named. The function is already named. Get me now?
Sir, scroll up. Let me see the answer for 1, 2, and 3. Supposed to be.
That's 1.
Okay. What's the next one?
That's 2.
Yeah.
And 3 is that one. 8x plus 3. And just be consistent and just in red.
Okay. Yeah, I'm getting that. Okay, so.
Cool. I'm actually waiting on you.
We'll finish.
Finish.
We're waiting on you.
Waiting on you.
Me waiting on you, you waiting on me. All right, fine. So since we're waiting on each other, let us go. All right, very good, guys. Now, as per usual, I'm very concerned, very concerned about those of you who, if I don't call upon you in class, you choose not to say anything. And I'm a teacher for too many years to sit and just figure that everything is hunky-dory. But there is coming a point when I am not going to say, Shedi, you're understanding? Aviana, you're understanding? Jermaine, you're understanding? I'm not going to do it.
Sorry,
really, Jermaine, like really, Jermaine, like really, my son, like really. Yeah, I know, but
I must still say something.
They want you to say something same way. Same way, sir.
Once I hear
No.
And if and the person I teach me, you know this.
Jermaine, and I know that. But guess what? Me want the company. Me want the company in that class.
Yeah, about 5 to 10% I keep a company in good money.
All right. Instead of 5 to 10 people, instead of 5 to 10 people, you know what I'm asking for do? Don't say nothing for about 10 minutes, and you're going to say how silent the class is. No, matter of fact, don't do it here. I want to talk to me here because I'm not going to get on the A. Jermaine, you go and ramp with me now. Because if you get a B plus, Jermaine, member said, I'm not going to put you, well, I won't be around for calculus to teach you, but although, Jermaine.
Hold on. Let's
Sir, run them serious there. Sir, don't run them serious joke there.
If you calculus 2, I'm stuck from now.
No, man, no good, man. Yes, please.
When you say not the role, what do you mean, sir?
Yeah, say it again.
When you say you're not going to be around, what do you
mean? Know, I was just thinking that I want a vacation. Maybe I'll just take a little time off and just go.
Yeah, man, after calculus 2, sir.
After calculus 2, you can take all the vacation.
You go on the beach and you just relax. Anyhow, come, let's go.
Yeah, man, after calculus 2.
After calculus 2. All right, I hear you. All right. Let's go. So I am now onto the power rule. So what we looked at earlier was a chain rule.
Sir, before you move on, one question. Sir, the one of the question did say f of x equal 5x minus 1 over 2x. Could the chain rule use for this too?
Give me the function again, honey.
F of x equal 5x minus 1 and over 2x plus 3. That question.
You see, once you have a fraction something that are a different function, different rule.
Okay,
but I'm gonna introduce you to all the rules tonight though, because I want you to be able to see the rules.
Wait, sir, did you get the answer for the fraction one?
No, I know. Negative 3x to the negative 4.
Okay, I'm gonna get that. Cool.
Nice. On to the power rule. No.
Sir, can I go back to the number 6 and I confirm something?
Okay, sure. Not a problem. Are you okay with it?
Sir, so meanwhile, she's
Yes,
looking
sir.
at that. I did hear the local connection with Kelvita did make. Cool. So once you have it being equal to the first determinant that D word, and you find in the second one, you just simply plug the same little formula where you give it into it to work it out.
All right, so now that you said, I was skipping over this because I was going to just give you this in the notes for you to look at it. But since you said something, let me just go to it. Come on, don't do this to me. Don't do this to me. Where am I? 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 Right here. All right, so given the function f of x equals to x cubed, when I differentiate this, I'm going to get 3x squared. We know this because we did that. So this denotes the first derivative. All right. If I'm going to find the second derivative, I'm going to differentiate the first one, not this one, you know. So in order for me to get the second derivative, I have to use the first. So when I differentiate this one more time, I'm going to get the second derivative. So this is going to be 2 times 3 is going to be 6. And I subtract 1 from the power, it's going to be 6x. So 6x is representing the second derivative. But I can differentiate the function one more time. The differential of 6x is going to be 6. So I'm going to be having the third derivative. You notice I have 3 little something up top here. So this now gives me the third derivative. So having the function here, f of x equals to x cubed, when I differentiate this function once, I'm going to get 3x squared. That's the first derivative. Differentiate the first derivative one more time, it gives me the second derivative. Differentiate the second derivative, is going to give me the third derivative. If I were to find the fourth derivative, what would be my answer?
0.
Why?
Constant.
Very good.
Constant is 0.
Very good. Very good. The fourth derivative would be a 0. Why, sir? Because the differentiation of a constant is equals to 0. Excellent, guys. Excellent. Very good. Very good. Proud of you guys. All right, the power rule. The power rule. As it suggests, the power rule has a power to it. But we have to be careful. We have to be careful with this one. We can't just...
Sir, stop share and share again. You never align properly.
Right.
Me don't wonder why keep over the song.
Okay, sorry. Better?
Yes, sir.
Okay, cool, thanks. Thank you for keeping me up to date. All right, let's go. Right, so as the power rule says, you have a power. But sir, the one you cannot look. So we're going to go to this. We're going to expand this first. No. Did I do a proof for you here? I hope I did a proof. If not, I have to go to the proof. No. Yes. No, I never did the proof. Yes, I did the proof. Good. Oh, sorry, on top of things, man. So let's go. So y is equals to 2x plus 5 to the second power. Find dy by this. This is a true question enough about maybe 5 marks. But you know the funny thing about it? They're not going to give that one alone. So you know, they're going to put something else in front of this, which is another rule. Then, sir, we can still remember all of them rules here. Yeah, man. I'll be using them so many times in class that you will know them on the back of your hand. Trust me. Hold me accountable for that. If it doesn't happen, tell me that I told you a lie. I have seen weak students come out of a calculus class, business calculus class, and know how to differentiate. And you guys are far from being weak. So, and I mean that from the bottom of my heart. So, trust me. Let's go. The same thing that we do, but we'll do it again, but with one more something. The 2-year spotlight. The 2 here, I'm going to use to multiply what is in front of this. See it here, so. Then I'm going to write about the 2x plus 5, and I'm going to reduce this by 1. See it here, so. Let me go again. The same something that we've been doing all along, or the same something that we're going to do now, plus one more step. This 2 is going to multiply in front of here, so. See it here, so. We write back this and put it to the first power, because this is 2 minus 1. See it right here, so. But what becomes important is that I must now differentiate what is inside the parentheses. I must now differentiate what is inside the parentheses. I must now differentiate what is inside the parentheses. In big school, this is not a decimal point. It is a multiplication point. In big school, this dot means to multiply. So what I'm going to be, it's going to be multiplied by the differentiation of what is inside the parentheses, right? I mean, this one so big, you can't say brackets, see? So the differential of 2x is going to be 2. See it right there, so? The 2 here. When I differentiate 2x, I get 2. When I differentiate positive 5, I get 0. Why again, sir? Because it's a constant. The differentiation of a constant is equal to 0. So this now constitutes my final answer. Hear what sir says, the story. Recall times 2 is obtained from the differential of what is inside the parentheses. Please note that we are required to differentiate inside the parentheses. But can I have something like that? Yeah, it is important. It is important that I know that we are required to differentiate what is inside the parentheses. So let me go through this again. When you're given the question, using the power rule, and that's why the power rule is very important. Me not ask you no question. Most of the something we then give you will contain the power rule. But the power rule is not difficult because the power rule takes into consideration all that I've done with you already, which is the chain rule. Of course, it did the first principles. But this 2 is going to be used to multiply what is in front of the parentheses. See it right here, so that 2 here. Then I'm going to reduce my power by 1. So it becomes 2x plus 1 plus 5 raised to the first power because it's 2 minus 1 raised to the first power. And then I'm going to differentiate what is inside the parentheses. I'm differentiating what is inside the parentheses. And when I differentiate inside the parentheses, I'm going to get 2. I can fix up this. This 2 times this 2. Remember that sign means to multiply now. Big school says this dot is a multiplication sign. So 2 times 2 gives me this 4. So it's 4 times 2x plus 5. And if I want, and the only reason I do this, normally I tell students not to expand. Normally I tell students not to expand for, or, when I say expand, you're going to use this 4 to distribute inside the parentheses. But for the purposes of the proof, I went ahead and expanded to say 4 times 2x is going to give me 8x. And 4 times positive 5 is going to give me positive 20. Now look back at the question. Question says 5 equals 2x plus 5 raised to the second power. And it asks us to find dy by dx. See here, the same question. Same exact question.
So before you move on to the proof, so is the case that we'll always have to use times 2? That
always have to use times whatever is inside the parentheses.
Okay. So because it's the 2x was put times 2, but the 2 doesn't actually times what is in the parentheses is times what is outside of it, over this side.
Nico, answer me this. What if this were 3x plus 5? What are we multiply this by?
By 3.
Good, very good. What if it was 10x plus 5? What I multiply this by?
10. But sir, the question is, but it don't, when you put times in it at the end, it don't really affect this because you put it back now the answer. Meaning it don't affect the 2x plus 5.
Because I multiply this number by this number here.
Okay, that's what I want to know.
Yeah, man, to get this 4 right here. And then it does affect it, Nico, because look at what happens now. This 4 times this 2x gives me 8x. And this 4 times this 5 gives me 20. So it does affect it.
Okay.
But I was taking it step by step. Very good question, but I'm taking it step by step. So let us look at the proof.
All right, hold on there, sir. Because it have each in the head first. Anika just make it tiny each little, but I have to make sure I get it right. So whatever is in the bracket needs to be multiplied outside. Me not talk your big terms, sir. Me I talk my little terms so it fit in my head.
Yeah, but except multiplied, you said differentiated.
Hold on, sir. When you reach the differentiation, we know it's a differentiation we attack. So whatever is inside the bracket that has the x will be multiplied outside of the bracket.
I don't want to see it like that. You know why I need Vito? Because this could have been 2x squared. And had this been 2x squared, you'd have to differentiate 2x squared. And when you differentiate 2x squared, what do you get?
4x.
4x. So this is going to be multiplied by 4x.
That would be 4 not multiplied by 4.
Right, then be multiplied by 4x, not just 4, but 4x. So remember, you are multiplying. Right, so you're multiplying by the differential of the inside of the parentheses. Did I say that?
Oh, you never said that.
P-A-R-E-N-T-H-E-S-E-S.
Then another question, sir. So that is you will be multiplied by the differential of inside. Is it that, sir, the inside will always be 2 terms or it can be 3 or 4 terms?
100. Any number of terms. Remember, sir,
So
don't know
is
what
it,
the question
is it then you're going to be using only that first term?
No, Kelvita, that's what I'm saying. Whatsoever the differential of the inside works out to be, that's what it is that you're going to be using.
Oh, it just click.
Yeah, man.
Just click.
So good question. I don't think that's getting annoyed with the question. I love when students ask questions. All I'm saying to you, I don't want to be prescriptive by saying to you, it's going to be the first term alone. You could have 3 terms in here, and each of the terms, or you could only have 1 term. I don't want to show you those yet because I know, and pretty much what it is that Onika just asked a while ago and what you're asking are questions that are actually jumping the gun, but I choose to answer, because I could have said to both of you, wait until I get there. But no, your brains are clicking, so I want to just continue with that vein. But I'm saying to you, in this case, I gave you 2 terms, 2x plus 5. But I'm saying to you, so Nika wanted to know if we always multiply by 2, and I'm saying no, because I don't know what the terms inside the parentheses will be. And then you are now asking, then sir, always 2 terms? I may say it could have been 3 terms, it could have been 1 term, it could have been 4 terms, it could be any number of terms them choose. But just remember, you'll always multiply by the differential of the inside of the parentheses every single time. So you have to differentiate the parentheses inside of the parentheses and then do the multiplication. Fair enough? Háblame.
Yes, sir.
Yes, sir.
Good job. Let us look at the proof. The proof says, where you going? Oh, I know what is the problem. I did everything as one. Yeah, come on. So what I'm going to do is, I'm going to cut this in 2. And then when I cut it in 2, I'm going to paste here. So I have a piece up on top and a piece on the bottom. Let's go. So I'm going to have 2x plus 5 all squares. But 2x plus 5 all squares is 2x plus 5 times 2x plus 5. Oh, sir, you're going to distribute one bracket over the other bracket. I remember this, sir. You're going to say 2x times 2x is 4x squared. Then 2x times 5 is 10x. And then 5 times 2x is another 10x. And then 5 times 5 is 25, sir. And then, sir, I see something again, because you can say this 10x plus this 10x is going to give me 20x. And I'll say to you that you're correct. And I'll say to you that you're correct. So I will now have 4x squared plus 20x plus 25. So what I would have done is to expand my 2x plus 5 all squares into this expanded term. Then now I'm going to differentiate this. Oh, sir. We see it. Sir, it is no longer a power rule. It now becomes the what? It now becomes a chain rule. Very good. It now becomes a chain rule. Then, sir, oh, that means you can move from one rule to the next? Yeah. Then, sir, then suppose me only know the power rule, we're gonna have problems. Yeah. So you have to understand all of the rules, because there are times you can get instead of 1 year, I could have used a different rule and work them 1 year. But I chose not to, because I was teaching the chain rule. So somebody from Montego Bay coming to college may use a different rule to do this, but you may convert it and call it x to the -7, and you get the same 100% that the student in Montego Bay, right? But by the end of today's class, sir is going to go through all those rules so you can see it. So when I reach here, so now I'm going to differentiate using the chain rule and not using a power rule again. Chain rule. 2 times 4 is going to be 8x plus 20. Yeah, 8x plus 20. Oh, sir, but hold on. Are the same 8x plus 20? Yeah, man. So I'm showing you that I get the same answer. Using both of them, using a power rule. So the point is, Anika and Kelvita, the point is, do you see the importance of multiplying by the differential of the inside of the parentheses? If I did not multiply by the inside of the parentheses, what I'd have only is 2 times all of this, and it would not give me the 8x plus 20. And the reason why it is important for you to differentiate the inside of the parentheses is because when you square these terms, 2x squared is 4x squared, and 5 squared is 25, you're missing this term inside your 20x. You're missing this term. So that's why you have to differentiate on the inside of the parentheses. You have to differentiate the inside of the parentheses every single time. I don't think I have another example here for you, because I want to move into the product rule first. Do one example of the product rule, then I'm going to move into, I may not even go into the other rule, the quotient rule, but there's just 2 other rules that are left. The product rule says the first times the differentiation of the second.
Scroll down.
All right now?
Scroll it. No, sir, I'm not seeing.
Yeah, I don't want to show you the rule just yet. I want to tell you the story first.
Okay.
Sir, the proof for the power rule was the second method?
Yes, was another method. So what I did, instead of using the power rule, I expanded and then was able to apply the chain rule to it instead.
Okay.
Yeah, man. So we're on to the product rule. The product rule says the first times the differentiation of the second plus the second times the differentiation of the first. Now, from my eyes were at my knee, going to little school, that story don't leave me. That story took me right through university and beyond. I want you to catch the same story. The first times the differentiation of the second plus the second times the differentiation of the first. Now let me just caution you on something here. The way I will teach you differentiation is going to be different from what you see on Educo. It's going to be different from what you will see in your other classmates' books or whoever else you know do calculus, and you may ask them to help with that one question, they may say, and also them learn it. I also learned it that way. But as a student, I found this way to be more understandable. And as a result of that, teaching CAVE or ADMAT or business calculus or calculus 1 or calculus 2, this is a method I use. It works every single time, and the story can't change. The first times the differentiation of the second plus the second times the differentiation of the first. The first times the differentiation of the second plus the second times the differentiation of the first. The first times the differentiation of the second plus the second times the differentiation of the first. But sorry, I have differential, same difference. Differential, differentiation, synonymous. So it's the first times the differential of the second plus the second times the differential of the first. So you will see in your books, they talk about U and V. I will show you U and V, but I want to show you this method first. Watch me. And I want you to watch me closely. Please. I beg you for your undivided right here, so. So this is a product rule. Product means that something multiplied by something. Rockstone, see the sir, me see it, you know. You see, sir. You see the first, and you see the second. I labeled mine the first and the second, and hear me out. To this very day, because when I was going to school, I had my pencil and my pen in my hand. There's no class time I don't go with my pen and pencil. And matter of fact, I always have colored pencils or colored pens, colored instruments. When I am doing my stuff, I'm going to write down which one I call the first, and again write down which one I call the second. You know why? So that I don't make any mistake. I again write down which one we call the first, and again write down which one I call the second, so that I know I don't make any mistakes. Very important. So important it is that we write over the question first, second. The first one, the second one. Watch me. The first, because I call it, I write it back. Times the differentiation of the second. It means now that I must multiply by the differentiation of this term. When I differentiate 5x minus 3, the differential of 5x is going to be 5. The differential of negative 3 is 0. So when I differentiate the second term, I only get 5. So I write it. So let's go with the story. It is the first, boom, times the differentiation of the second, boom. The first part they're done. Then it says plus the second. We write back the second, see that? 5x minus 3, boom, times the differentiation of the first. And I no need to differentiate the first. Differentiating the first, I'm going to say 2 times 2 is 4. 4x to the first power, I'm just going to write 4x. Differentiation finish right here. So real talk. Differentiation finish right here. So all that is left right here says algebra. Everything that is here is me fixing up the something algebra. Let's go through the differentiation again. The rule says the first times the differentiation of the second plus the second times the differentiation of the first. The rule says the first times the differentiation of the second plus the second times the differentiation of the first. The first times the differentiation of the second plus the second times the differentiation of the first. Watch me. I'm going to label my first, and I'm going to label my second. Then, sir, you couldn't call this one the first one and this one the second one. Absolutely.
Hold up, sir.
Somebody in the chat said they're not hearing. Oh, who not here? Andrew.
Check him like Andrew. Check him. Well, he never hear me.
Sasha would be Mike, him speak. I need to check if him not hearing.
In there. And the,
Yeah,
and
I'm sign out and sign back in. Am I here now?
okay, cool.
All right, so what I'm gonna get is that the first, you write it back, right?
Mm-hmm.
That's what I heard. And then you differentiate within the brackets, you get back the 5.
No, not in the brackets. You differentiate in the second term.
Oh, yeah, the second, which is
Right.
the 5x,
Which is
when you get when you get the 5, right?
Plus?
That's all I heard. I didn't get
Okay,
anything
all right, no problem. Great, no problem. You were hearing fine up until your internet broke. All right, let's go. So what I'm saying to you, you're given the question, you will know that it's a product rule because somebody will say, sir, how you know the product rule is different from the chain rule? You know, say 2x squared is being multiplied by 5x minus 3. Sir, how you know that? Once you see them bracket here, so you know, say them bracket here, so I separate the 1 year term from a 1 year term. So you know multiplication, or you should know what multiplication looks like. The chain rule is separated by plus signs and minus signs. So when it's a plus sign and minus sign and no multiplication in there, chain rule. Think of the chain, and that's why I asked you to look at the chain around your necklace, you know, to see what it looks like. Let's go. So I'm calling this one my first. I'm calling this one my second. No, I never call this one my first and this one my second. You know why? Because me read from left to right. Next thing I go call this my first. I'm gonna mix up the something and go get the question wrong. Not that if you call this the first, it's not going to get it out, you know. But wait until it gets a little bit more mature with this stuff. And by the time I reach maturity, you're going to always call one of the first. Let's go. The first. You see when I say the first, you write it back. Andrew, present, sir. The first, present. Write it back. 2x squared. Times the differentiation of the second. You see when I put these parentheses, it means that I'm multiplying. That's why I put it in parentheses. Times the differentiation of the second. So it means that I have to differentiate my second term. When I differentiate my second term, the differential of 5x is 5. The differential of negative 3 is 0. So all that is left here is only 5. And Nika will say, but sir, that may I ask you, is only 2 terms always getting there? No. But in another 1 year, only 2 terms you get. So anything in the second term, you're going to differentiate it and we get that 1 year. So it's the first, this, times the differentiation of the second, this, plus the second, which is this, see it here, so, times the differentiation of the first. Then I'm going to differentiate the first now. When I differentiate the first, I'm going to get 2 times 2 is 4, see it right here, so. And I reduce the square to 1, so it's going to be 4x right here, so. Differentiation finish, whoops, right here, so. All that is left here is my algebra. One more time. The first, this, times the differentiation of the second, bam. Plus the second, this, bam. Times the differentiation of the first, bam. So having done that now, I am going to fix up. And when I fix up, I can say 2x squared times 5 is 10x squared. 4x times 5x is going to be 20x squared. And 4x times negative 3 is negative 12x. And this squared, x squared, and this x squared are related. So we can say 10x squared plus 20x squared are 30x squared. The minus 12 stands alone, so I just put back the minus 12. Then I can say to myself, what is common here? That is common there. And I recognize that 6x is common. So I draw out my 6x, and then I say, what is left? 6x times 5x gives me 30x squared. And 6x times negative 2 gives me negative 12x. So I just factorize to just make it look more presentable. That's the end of the question. That's the end of this question. All right? Now, what I want to do is, I'm going to give you something to do in class, you know. Like that one there, I don't want to go through that one. What time is it now? 9:38, I can go through it. What I want to do is to introduce all the laws to you so that when I'm giving you some work, all right, so I have 3, okay, the quotient rule comes out. So let me do this one here with you. Go ahead, please.
Well, Yannick was up before mine.
Oh, sorry, Yannick. Go ahead, hon.
So, sir, essentially, the product rule can be used when you have two terms, meaning like you have that on the outside and you have something in a brackets.
Very good. What shall be so?
But I kind of the same thing she asked, but I was going to spin it a different way. Is if would it work if there are three terms? So the first, the second, and the third would or it just has to be two terms.
Okay, so if you get three terms, you have to combine two of the terms so you can have first and second, because the product rule is it first and second. So very good observation. And this is one of the things that I keep saying to the class. We're not even pay German, man. I am sure others of you have questions that are coming up that can benefit the class. Ask the question, put the question on the table, so that when you're listening to the recording again, you can say no, say are true. Because I mean, very good observation, guys. Thanks, Kavita. Thanks, Yannick. Thanks, Andrew and Charlene and the rest of them that have talked to me. Let's start.
Sir.
Yes, please.
Sorry,
Yes,
let's go back to the example, please.
Show them, Chedi.
You can go back to the example, the one that you just did.
Okay, sure, honey. So hold on there. So the first time you talk to me in the class tonight, that you ask me to do, come ask me a question, Chedi.
No, I don't have any questions, sir, but I just wanted to, I was kind of just doing it again out of my head. I just wanted to make sure because I didn't get the last part. I didn't write on. That's all.
Nice, girl.
Sir, you can show me how you got the 4x again?
Differentiating the first term. When I differentiate 2x squared, I'm going to get 4x. This 2 times this 2 is 4, and I'm reducing the power by 1. So when I differentiate the first term, I get 4x.
Sir, I have a question. How much would a question at this value?
About 5 marks, you know.
5 marks? And continuing this question, sir, you said that the right in the blue, that's where differentiation ends, right, sir? So, sir, can I stop there, or do I have to do in what's in the black and red?
You can't stop, you know. But guess what? You can't stop, you know. But best believe says on that point alone, you can get the marks for.
All right, thank you.
Let me make a notation, but I don't think I need to. The point I was making, was that Krishna?
Oh,
yeah. No, sorry.
Lambert. Lambert.
Oh, Lambert. Okay, Serene. All right. Yeah. Thanks for, so you see, yeah, you need to talk so I can use the voices to differentiate. Yes, Lambert. The point I was making, Papa, is how it goes. So you cook oxtail and rice and peas. So you cook it, and then you just put it in a container, and then just like how I don't remember who it was. Oh, it was it Onika who I try to leave out, and I don't know where she go, and see one bus and I run on the bus, and the food shake up. And when you get to the destination, you open it and present it to somebody. They may not want to eat it. Not that the food is not properly cooked, but the presentation is off. No, me that eat it same way, because the food it name. And when you share up in the plate, I mix up everything together nonetheless. But what I'm saying to you is just a presentation. So the differentiation ends here. The cooking done is how you plate the food now. The rice one side, the vegetable one side, the meat one side, the drinks one side. Yeah. So don't leave it here. If you leave it here, that's when you get the mark for this portion. But best believe, when I say to you that the question carries 5 marks, it's not just 5 marks for the answer alone. There are different steps in the question that you get marks for. Different steps in the question you get marks for. So this, which brings me, thank you, Celine, for the question, which brings me to another point. When you're doing your question, students, you need to show me your working out. I'm not one of those teachers who map for answers. I want to see your working out. Worked out. Let's go. Numero dos. Numero dos. It says, the first times the differentiation of the second. Oh, sir, this one looks like the one before, you know, sir. Oh, but sir, this one half cube, sir. The one kind of tricky, you know. Sir, run it. It's the first. Krishna, present, sir. The first. You write him back. Times the differentiation of the second. Now it is that we start to differentiate the second. But we know when we differentiate -3, we can get 0. So all we're differentiating now is just x cubed. And when we differentiate x cubed, we know that, sir. We just said a while ago. 3x squared, sir. Bam. Then plus the second, x cubed minus 3. See just so? Times now the differentiation of the first. So I now need to differentiate the first. 3 times 4 is 12. And I subtract 1 from the power, we can get 2. So it's going to become 12x squared. So let's go again. The first, bam, times the differentiation of the second. The differentiation of x cubed is 3x squared. Plus the second. So I'm writing back everything here for the second. Times the differentiation of the first. I'm going to differentiate the first. 3 times 4 is 12. And I'm subtracting 1 from the power. So it's going to become 12x squared. So I have 12x squared. My differentiation ends right here. All I'm going to be doing now is just fixing up. 4 times 3 is 12. X cubed times x squared is x to the 5th. Oh man, I keep doing that. I keep doing this in class, but let me just do let me separate something for you and show you what it is. I'm trying to make the notes simpler for you guys, so cut. And then I'm going to paste, and then I do that, and then I cut this, and then I come here, and I do that, I paste, and then I say recall. So I want to recall that when I'm multiplying, and the bases are the same. Oh, Lord Jesus, what did I do? Oh, I had copied this. I want to cut you. When I'm multiplying and the bases are the same, I'm adding my powers. See, if you recall, a to the m multiplied by a to the n. A to the m times a to the n. Because the bases are the same is, I'm going to now have a to the m plus n. So once I'm multiplying and the bases are the same, I'm adding my powers. Once I'm multiplying and the bases are the same, I'm adding my powers. Another name for power is exponent. Another name for exponent is sorry about that. Another name for exponent is index or indices. Index is singular and indices is plural. Index is singular and indices is plural. So let me give you the narrative here. So the narrative is, when you are multiplying and the bases are the same, you're adding your exponents or your indices. Very, very important. You add the powers, the exponents or your indices, all mean the same thing. Sir, why are you telling us that? This x cubed times x to the second, the bases are the same, x's, so you add 3 plus 2 to give it this 5. All right? 12x squared times x cubed is going to give you 12. This x cubed times x to the second power. 2 plus 3 again is 5. And negative 3 times 12x squared is going to be negative 36x squared. So just remember, whenever you are multiplying and the bases are the same, you add your powers or your exponents or your indices. All right? Then you look to see now that this 12x to the fifth and this other 12x to the fifth are exactly the same family. So you can add them together. So you're going to get 24x to the fifth minus 36x squared. What do I have here? 24x to the fifth minus 36x squared. And then you can factorize. And when you factorize, you can get what is common here, that is common there, is going to be 12. And what is common between x to the fifth and x to the second power? I often say to the students, you will subtract the smaller of the two. Hint, S-U-B-T-R-A-C-T, subtract the smaller. Subtract the smaller of the two. It's just a hint. Subtract the smaller of the two. Yeah, look at it bold, so you're not bold. All right, so look at this now. So hint, subtract the smaller of the two, and that's it. All right, so we have 10 minutes left, 9 minutes down. I have other questions to give you with the solution, but I just want to go through the last story. And the last story talks about the quotient rule. Don't think that I'm not going to go over it, you know. It's just that I want to give you all the rules because I want to be able to send you some questions with mix up, with the chain, the product, the quotient, and the power rule. The quotient rule says the denominator times the differentiation of the numerator minus the numerator times the differentiation of the denominator all over the denominator squares. The denominator times the differentiation of the numerator minus the numerator times the differentiation of the denominator all over the denominator squares. One more time. The denominator times the differential of the numerator minus the numerator times the differentiation of the denominator all over the denominator squares. Watch me. Watch me. Y is equals to 2x over x plus 1. Quotient means to divide. The quotient rule means that you are dividing. It means then that you're supposed to have a numerator and a denominator. So whenever you see a fraction, it means that you're using the quotient rule. Whenever you see a fraction, it means that you're using the quotient rule. All right? What the quotient rule says, it is the denominator times the differentiation of the numerator minus the numerator times the differentiation of the denominator all over the denominator squares. Watch me. The denominator present. You call him, you write back the name. The denominator present times the differentiation of the numerator. When I differentiate the numerator 2x, I'm going to get 2 c here, so minus the numerator minus 2x times the differentiation of the denominator. When I differentiate positive 1, I get 0. When I differentiate x, I get 1. So this is a 1 inside here. It's the denominator times the differentiation of the numerator minus the numerator times the differentiation of the denominator all over the denominator squares, all over x plus 1 all squares. Then, sir, you have to expand all of that? No, sir. Just write x plus 1 all squares, and you leave it at that. So let's go. The denominator times the differential of the numerator minus the numerator times the differential of the denominator all over the denominator squares. The denominator, put it back, times the differentiation of the numerator, you put it back. Differentiate it and put it here. minus the numerator. You can put it back. See 2x, 2x. Times the differentiation of the denominator. When I differentiate x plus 1, I'm going to get 1. All over the denominator squares. Differentiation ends right here. So differentiation ends right there. So what is left is just the algebra. Let's go. So, sir, I can cancel this one with this one. No. Remember when we're in the intuitive approach, we had this error and I spoke to you about it. You can't cancel beside a negative sign. It has to be a multiplication sign. So you have to go work out up here first. So 2 times x gives me 2x. 2 times 1 gives me 2. And this one times negative 2 gives me negative 2. The negative 2x cancels with the positive 2x. I'm only left with 2 in the numerator. And I arrive at my denominator and the question done. The denominator times the differentiation of the numerator minus the numerator times the differentiation of the denominator all over the denominator squares. I am going to stop here for tonight. I would have introduced to you 4 rules: the chain rule, the power rule, the product rule, and the quotient rule. I would have done at least 1 question on each of the rules. Sir, why? Because I want to send you this document in another few minutes after class so that you can have these examples. I choose to do the solutions. It don't make sense. Ouch. It don't make sense. I just leave the question. Well, I find, I'm thinking as a student that, when I get the question with the answers, at least I can do it and know if I'm on the right track instead of waiting to come to class or calling certain answer. I chose to do some questions here, right, on the quotient rule. Now I'm going to leave the quotient rule here with you with these worked examples, and I'm going to give you some other examples now that I want you to try on your own without the solutions, and then you're going to try as best as possible. Let me just say to you that I know it is a lot of work that I presented tonight, and I have to use my Thursday to present as much as possible so that you can use the weekend in trying to get some work done up. For those of you who joined late, mid-semester begins next week for 2 weeks. There's so many things that I have to be doing now. I am preparing more notes for you. I am doing the registration for those students who just got their CSEC results. I really don't have time to sit with you in preparing for the mid-semester the way I want to. So the mid-semester is going to be not next week, but the following week. So this is what I want you to do for me, guys. Over this weekend, you're going to do your preparations. You're going to be doing your whole preparations. On Tuesday, all being well, God sparing life, we will decide which of the days next week, either Tuesday or Thursday for the exam, right? I know most of you will want to choose Thursday because at 5 o'clock, you're only still trying to get home. And I know by Thursday at 7 o'clock, most of you are already home. But we can work it out. It's not a problem. Whichever day is good for me. I would use some of next week to go through some more examples and past papers to help you prepare for the exam. But best believe the greatest preparation is going to be the work that you would have put in. I have placed all the Zoom recordings into my YouTube channel. I'm recognizing I'm seeing 13 views at most. There are 20 plus of you in the class. Utilize it for this weekend. Make good use of it. Drop your questions. There are classmates who are very capable to answer. I see those questions. If I don't see the answer come out, I can chime in. But please do your preparations. All right, me don't talk now. That's the final thing I'll say for the night. You ask me whatever you need to ask me now. Are there any questions?
Sir, so basically, whether or not you like it, the chain rule tend to come out in all of the other rules.
Talk truth. Talk truth. Yeah, man. Yeah.
That is
And a little-
one.
Go ahead, Sudhi.
Two, did you get to take out what you need to take out of the first set of homeworks on Edicasa?
Crap. Please to remind me. Please to send me a reminder over the weekend, Yanni. Oh crap. Please remind me over the weekend. Please and thanks. But you said something a while ago, Yanni, that I want to just is when you get a little bit more mature in doing the different rules. It's like all this one, I can convert this one into a product. All right. So it's just like how I converted the 1/7 into something else, 1/x to the 7 rather into something else. I can use this very law to convert the one that I just showed you a while ago into a product. So sometimes you get the question and you may feel comfortable using another rule. If they say to you specifically use the first principles, you have to use first principles. No matter of fact, I wouldn't even want to give you a question like this to use first principles to do this. X plus h to the 7th power. Nobody got time for that. All right. So the only time you'll use the first principles is unless they specifically say to you, Unique, use first principles. Outside of that, don't use it. That's our secret. Any other question?
Sir, you never had me on Educasoft.
Oh, Krishna, I need to double check. Let me just write it down. I'll double check for CHRIS.
Sorry, can you check that for me as well?
And you to Andrew?
Yeah, I can check that for me as well, and I don't even know how to even access it.
Well, just so much honor, Anthony. All right, who else? All right, so Krishna, Andrew, and Arlene, I will do that for you. All right, it's 10 o'clock, and I want to be true to my time. I don't want to keep it beyond this. Go get some sleep. Get some sleep and see if I can get up a little early before work tomorrow.
That now work.
Tell me to leave me alone. All right, guys.
Sorry, just before you continue, all of those persons who said that they're not on Educasoft yet, you're in the WhatsApp group?
That's a good question. Awfully, Andrew, Krishna, in the WhatsApp group?
Yes.
Okay, good. All right. Big up yourself. Have a nice day, guys. I enjoyed my class tonight. I hope you did too.
Yes, sir.
Bye, sir.
Bless your heart. Take care, guys.
Stress.
You'll be fine. I promise you. Later, man. I'm here to support you. Okay, sleep tight. Don't let the bed bug bite. Say your prayers.
More like much nightmare, sir, not the bed.
Bye, sir.
See you, dearest. Take care.
Just throw out all the palettes and give me tonight. What is that?
I love it. Say we can beat her. There's nothing that can change the love. Osh.